In this video, we will consider models where the dependent variable y is binary. Sometimes we can only observe whether an event happened or not. For instance, if we study what types of firm export, what makes some low-end applications accepted and others not, what determines a person's decision of attending a university, what makes a revolution successful. There are two possible outcomes for these dependent variables. We only observe whether a firm exported or not, whether a loan was denied or approved, whether a person went to the university or not, and whether a revolution succeeded or not. How does the linear regression models change if now the dependent variable y is binary? We will see that in models with the binary dependent variables, the regression function can be now interpreted as a conditional probability of an event, which corresponds to the case that the dependent variable takes the value of 1. We can also think of it as a successful probability. Let's first check what will change for the linear regression model if y is binary. Here is the population model for a simple linear regression. Under the conditional zero mean assumption, we have the population regression function. The expectation of y conditional on x is equal to beta 0 plus beta 1 times the x. When y is binary, we have that the conditional probability of y equal to 1 is the same as the expectation of y conditional on x. So let's check why this equation holds. If we want to calculate the expectation of a random variable of y, we need to know the value of this random variable y takes and the probability that this random variable takes this specific value, small y. When the dependent variable y is binary, it means we have either the case that the dependent variable is 1 or the dependent variable is 0. And this probability y equal to 1 conditional on x, for the event y equal to 0, the probability is 1 minus the probability that y equal to 1. Then we have the expectation of y conditional on x is equal to 1 times the probability that this event happens plus 0 times the probability that the other event happens. What left is the conditional probability of the event that y equal to 1. So in other words, the probability of the event that y equal to 1 is the same as the expected value of the dependent variable y when y is binary. In general, we have 3 different ways to model the conditional probability. Suppose we directly let the conditional probability of y equal to 1 be the population regression function, which is a linear combination of independent variables and the parameters. We will have the linear probability model. If we let this conditional probability to be a normal distribution, the value of this distribution is the same as the value of this linear component. We will have the probit model. Similarly, if we let the conditional probability be a logit distribution, we will have the logit model. Notice that all three models share the same linear combination of parameters and independent variables. The difference is that this linear component determines the conditional probabilities in different ways. In the linear probability model, we directly treat this linear combination component as the probability of the event that y equal to 1. In the other two, we transform this value into probabilities with either a normal or a logit distribution. Later we will see the differences. For now, we will focus on the linear probability model. For the linear probability model, the population regression model is the same as the before, but now we denote the arrow term as E to distinguish it from the standard OLS regression where the arrow term is denoted as U. But the arrow term E still satisfies the conditional zero mean assumption. As we showed before, that the population regression function is the conditional probability of the event that y equal to 1. This conditional probability is also called the response probability or the probability of success. The parameter beta j measures the change in the probability success of y equal to 1 with respect to the change of the independent variable xj when holding all other factors fixed. This interpretation is comparable to the standard OLS regression, that the change of the expectation of y is the same as the beta j times the change of xj. But now this expectation of y is the same as the conditional probability of y equal to 1. To estimate the unknown parameter, we're still trying to find a fitted value through the sample regression function. The difference now is that the fitted value y hat is the estimated probability of the event that the observed dependent variable y is 1. The estimated coefficient beta j hat is still to give us some idea about the true parameter beta j for the population model. The question is, can we similarly estimate using the OLS method? The answer is both yes and no. For the binary dependent variable, we do not have the assumption of homoscedastic arrow terms. But luckily, the OLS method is still valid with some adjustment. We need to use the robust standard arrow to correct heteroscedasticity. In the next video, we will learn about this topic in more detail. For the case of binary dependent variable, let's first check where the heteroscedasticity comes from. According to the population model, the arrow terms take two values. If the dependent variable y equal to 1, then the arrow term is 1 minus this linear combination term. And the probability for the arrow term equals to this value is probability that y equal to 1 conditional on x. If y equal to 0, then the arrow term is minus this linear component, and the probability for the event is probability y equal to 0 conditional on x is 1 minus the probability that y equal to 1. Suppose we denote this linear combination term as a big M. First, notice the expectation of the arrow term is 1 minus this m times the probability, which is m, plus minus m times the probability 1 minus m which is equal to 0. Then the variance of the arrow term is the expectation of E squared, which is 1 minus m squared times the probability, which is m, plus minus m squared times 1 minus m, and it is equal to m times 1 minus m, which is this term here. Notice that the variance of the arrow term will be different for different values of the x. This means that except in the case where the probability does not depend on any of the independent variables, there must be heteroscedasticity in a linear probability model. What's the consequence of heteroscedasticity? We learned in previous lectures that the assumption on the variance of the arrow term does not affect the unbiasedness of the OLS estimator, but it is quite important for the efficiency property. If we have heteroscedasticity, the standard errors for the estimates are biased, and therefore we cannot use the standard t-statistic, f-statistic confidence intervals to do the hypothesis test, even in large samples. With heteroscedasticity, it turns out we can still use OLS method, and it is quite easy to correct the standard errors for the heteroscedasticity. Let's first check an example for the linear probability model. We use the data HDMA. It documents the mortgage applications filed in Boston in the year of 1990. The dependent variable deny is 1 if the mortgage application is denied, and it is 0 if the application is approved. The independent variable is the PI ratio. It is the size of the anticipated monthly payments relative to the applicant's income. Then it's quite straightforward to translate the relationship between the PI ratio and the mortgage denied decisions into this simple linear regression model. Here is the regression results. This coefficient is beta 0 hat and beta 1 hat. We are often interested in the coefficient beta 1 hat and the fitted value y hat, because now the y hat gives us an estimate for the probability of the event that y equal to 1. According to the estimation results, a 1 unit increase in the PI ratio is associated with an increase in the probability of a loan denial by 0.604 on average. We can also calculate the fitted value y hat. It is equal to beta 0 hat minus 0.08 plus the beta 1 hat 0.604 times, if the PI ratio is 1, then we get around 0.5. So it means a PI ratio of 1 is associated with an expected probability of mortgage denial of roughly 50%. As we discussed before, when the dependent variable is binary, there is heteroscedasticity. The estimated coefficient under heteroscedasticity is still unbiased, but now the standard errors are problematic. Therefore, the t-values and the p-values are also not valid anymore. What we can do is to correct this standard error with a robust version of the standard errors. We can simply use the coefficient test function in R to obtain the robust standard errors for both coefficient estimator. Here is the command. The first argument is the name for the OLS regression. The second argument is the variance-covariance matrix with heteroscedasticity adjustment, and this type is the method for the adjustment. The coefficients are the same as the before, but now the standard errors are different. Given these robust standard errors, we can similarly calculate the t-statistic, f-statistic, or the confidence intervals and use the p-values to do hypothesis test. So the t-value and p-values here are valid now. This figure gives us the estimated probability of mortgage denial for different levels of PI ratios. The dots are the observations. For the same level of PI ratio, some applications are approved with the outcome 0, and some are denied with the outcome of 1. Similar to the OLS regression, we tried to fit the data with a linear line. Based on this fitted line, we can calculate the estimated probability of mortgage denial if we know the PI ratio for an applicant. Notice that the predicted probability can be less than 0 or larger than 1. It is not a big problem if we are interested in the predictions far away from these two extreme values, or we are only interested in identifying that PI ratio and the mortgage denial decisions are related. But if we also care about the estimated probability, we want to know for a specific applicant for a certain level of PI ratio, what's the probability that his application will be denied. Then we may have problem because a probability smaller than 0 or larger than 1 is clearly unreasonable. In this case, we may consider probit and logit models. The idea is that we can transform this linear line through normal or logit distribution to make sure that the fitted value is always bounded between 0 and 1. Here we will only very briefly discuss the probit and logit model. As we introduced before, in the probit model, the conditional probability is equal to phi z, and this z is the population regression function, and this phi is the CDF of a standard normal distribution. In the logit model, the conditional probability is equal to fz, and this fz is the CDF of a standard logistically distributed random variable. Compared to the linear probability model, now if we want to predict the probability of the event that y equal to 1 given the x, we first need to compute this z. This term is directly equal to y equal to 1 conditional on x in the linear probability model. But for the probit and the logit model, we also have the second step. Then we calculate this z and we look up this phi z or fz based on their CDFs. The distributionally transformed value gives us the probability that y equal to 1 conditional on x. We use the function glm in R to run the probit regression. The first argument is the same regression formula. The second argument is to identify the family, which is binomial for the binary dependent variable, and the model is probit. The summary of this probit model gives us the regression results. We similarly use the coefficient test function to get the robust standard errors. Again, the estimated coefficients are the same as the before, but now the standard errors are different. Given the regression results, we can also calculate the estimated probability of denial for each level of PI ratio. And compared to the previous linear probability model, now this estimated conditional probability is nonlinear. Due to this nonlinearity, we often do not directly interpret the coefficient beta 1 hat. Because now the 1 unit increase in the independent variable x may have different effects on the probability depends on the value of the x. For instance, the marginal increase in the probability is very small when the PI ratio is very small or very large, but if the PI ratio is in the intermediate level, the marginal increase in the conditional probability is very large. Instead, with the probit model, we often care more about the fitted value, which gives us the estimated probability of y equal to 1 conditional on x, and this fitted value can be obtained from this stretched S-shaped function, and it is always between 0 and 1. The regression for the logit is very similar. We still use the GLM function, but now the model should be specified as logit. And we also use the coefficient test to correct for the heteroscedasticity. The dashed line here is the estimated regression function for the logit model. It also flattens out for large and small values of the PI ratio, and it also has a stretched S shape, but it's steeper for the intermediate level of PI ratios compared to the probit model. Given the coefficients for logit model, we can similarly estimate the probability of a low-end denial for a specific level of the PI ratio, and this estimated probability is higher on the logit model than that under the probit model. It is often not obvious how to decide which model to use in practice. The linear probability model has the clear drawback of not being able to capture the nonlinear nature of the population regression function, and it may predict probabilities to lie outside the interval of 0 and 1. However, linear models are much easier to interpret because the coefficient beta 1 captures the fixed marginal effect. The variables that are statistically significant in the linear probability model are typically also significant in nonlinear models. The probit and logit models are harder to interpret, but capture the nonlinearity better than the linear approach. Both models produce predictions of probabilities that lie inside the interval of 0 and 1. If we are only interested in whether a variable is significantly related to the dependent variable, linear probability model should suffice. If we want to make predictions, or if going from 1 to 2 is conceptually different from 2 to 3, a nonlinear model may be better.